Hi grade 12s, good to be with you again. We're doing organic chemistry today and it's all about reactions. Now make sure that you understand how to name and identify features of different organic molecules before you get into the reactions, because you'll see that often questions in the exams ask about defining and writing down the names. You need to know that really well. The reaction section is not as involved, but you do need to know some basics. Let's check out our checklist. So the checklist is quite short, but I want to expand on it a little. It basically says you need to be able to identify different types of chemical reactions involving organic molecules. Now, so what are the fundamental basic ones that you need to know? The first one that you need to take note of is what we call an addition reaction. So what happens here is that we have an unsaturated hydrocarbon. And what do we mean by that? Unsaturated means it hasn't got all its bonds. It can take some more. For example, it could be an alkene, or it could be an alkyne. So in either of those cases, alkene or alkyne, if you look at them carefully, what you'll recognize is the number of partners that this carbon here has. It's only really got a partner over here, which I'm going to call X, and another partner over here. That's only two partners. It needs to have three partners. It needs to have four bonds to different atoms. At the moment, it's only got two. So where you look at this one, it's got, in the alkyne, it's got a partner over here, let's call it Y, and it's got a partner over there. So it is also deficient. It hasn't got enough partners. In fact, I can see I've made a little mistake over here. This one needs to have an extra partner because it needs to have four bonds. So it can have a partner of Z over there. So you can see over there it's got three partners. Over here it's only got two partners. Still doesn't have the maximum number of partners. Each bond isn't a single bond. For that reason, we can take the structure of that bond and we can add to it. And what happens is we take something that's an oxidizing agent, typically something like a halogen, and that second bond, and I'm just going to use the example of ethene, the second bond can break, and when we take something like bromine, we add it to that, what happens is that second bond, which is different in its structure, you don't really have to know that, but it is a different type of bond. It's got more delocalized electrons. The bromine can get in there and break it, and we think about it like a bridge lifting up. So the two halves of the bonds lift up so that the bromine can sit on it, and we get the situation that we get going from an alkene, like ethene, to something like this, which we would call dibromoethane. And if I wanted to be really correct, I would call this 1,2-dibromoethane. I hope you can see that we've gone from being unsaturated to being saturated. Let's just check that terminology. Notice that this carbon that I've circled in yellow now has a partner over here, that's one partner, a hydrogen as another partner, a hydrogen as another partner, and a carbon as another partner. It has four partners. That's why it is saturated. It can't take any more partners. And all the carbon atoms in the molecule are just like that. So that's addition. And it happens for unsaturated substances, and usually happens under normal conditions. At room temperature, doesn't really require much persuasion. Obviously depends on the strength of the oxidizing agent. And you can do it with water, you can do it with any of the substances that even hydrogen works quite well to hydrogenate. When we're describing that addition reaction, we can either say it's addition, it's halogenation, because it's making a haloalkane, or we can even say hydrogenation, because it's adding it, or chlorination, or bromination, iodination, iodonation. So we're adding iodine to that substance. So that's the addition story. Now, the next ones are opposite of each other. They're reverses of each other, if you want to have a look at them like that. The one is, it's the reverse of addition. Let's do the reverse of addition. We call this elimination. Now, with addition, what I want you to notice is that we start with two reactants. We start with two reactants, the bromine and the ethene, and we end up with one. With elimination, what happens is the opposite. So we could take something that is an alcohol, like that, ethanol, and we can eliminate from that alcohol two things, from that point, and we could go back to producing our ethene and end up with a second product known as water. This is eliminating a water molecule. It's a type of hydrolysis, taking water out. And so we're forming the double bond again. So where addition makes the double bond, we're forming it in elimination. We're removing something, and we're leaving the product, the reactant, to form those products. So elimination, the opposite or the reverse type of reaction, we're starting with one thing and we're ending up with two. Elimination. Last one is the signal that we would see on the side of a soccer field when somebody does that. They're meaning substitution time. And in chemistry, we could do just the same sort of thing. We could take an example, and I'm going to just put the substitution sign here. Just write it in, substitution. And we could take something and simply replace it. So we could take something like, let's use another one. Take an alcohol and let's react that with something like bromine, and in its place we could get something like the brome. I've not put in all the bonds, sorry. I need to put in all the bonds to make sure I've got the right number. And we're just simply taking the place of this hydroxyl group. The bromine is stronger, more oxidizing, and it will fit in over there. And we would, even at this point, be able to do more than just that. It would probably go further, because we would have the bromine sitting over there. And what are we left with on this molecule? Well, the hydrogens fit in there, hydrogen fit in there. And what's going to happen to the things that have replaced? Well, they're going to join together, and we're going to get a product that is water as well. So if you take a look at that, bromine's gone in, and it's taken the place of both the bromine and of the hydroxide, or the hydroxyl group, not hydroxide, hydroxyl group, and the hydrogen, and it's got substituted in. So, and this can happen if it was hydrogen bromide, it would have just taken the place of the hydroxide group, and we could do a whole number of those sort of substitutions. Now, the conditions of those you need to know very carefully, and under what conditions. It usually requires heat, usually requires something that's quite a reactive substance, like concentrated alkali, potassium hydroxide or sodium hydroxide, when we're dealing with these sort of reactions. So be aware, do some learning, make sure you've got it right, and that you can understand where things are happening. There are two other groups of organic reactions that I want to mention. The one is oxidation, and this isn't although it's similar to the redox idea. What you need to recognize for organic chemistry, you're not going to have to count the number of electrons changing, but you do need to know that if you undergo oxidation of an alcohol, the alcohol will oxidize to form, so if that was the functional group, it will form the carboxylic acid as its final product. But in between, it can also form, depending on what type of alcohol it is, it can also form a ketone, an aldehyde. So it can form that, which is the aldehyde at the end of the branch. But if it was in the middle and this was a secondary alcohol, it would form the ketone. So you can get three things from the oxidation of alcohols. Remember that these do come up, and you do need to understand the difference between primary, secondary, and tertiary alcohols, and perhaps you just need to revise a little bit about that. The other example that you might be familiar with a reaction, a type of reaction that you need to revise, is esterification, where if you take an alcohol plus a carboxylic acid, you get, in the presence of concentrated sulfuric acid, which acts as the catalyst, you will get an ester plus water. Very important that you go through that and you understand exactly what's happening there. The final one, which hasn't been asked for a long time, but it could actually come up in the exam, is something called combustion reactions. So we could take combustion. If we take a ordinary hydrocarbon, something like, even use the simplest one, ethane, which would be, that's right, C2H6 plus oxygen, it will burn in that substance, in there together to form carbon dioxide and water. Now the tricky thing with these type of reactions is that you need to know how to balance them. I'm not going to balance that particular one, I'm just mentioning it. You need to make sure that you've gone through all of these different type of reactions. Now, let's go and have a look at some previous exam paper questions just to make sure that we're up to speed and we can revise this section. So the first question we're going to do is taken from the November 2013 paper, and it happened to be question 5. It tells us that we've got two straight chain compounds, P and Q, and each have the following molecular formula. See how important terminology is with organic chemistry? You need to make sure that you understand all of these terms very well. So P, C4, H10, what homologous series does that belong to? Well, 4 times 2 gives me 8, plus 2 is 10. So I know that this is an alkane. Even before I've read any more of the questions, I'm going through and I'm making a mental note in my head what's going on. And Q, C4H8, I'm going to say that's an alkene, because the general formula fits the pattern of CnH2n plus 2, and this one fits the pattern of CnH2n. So we've identified that these are two different homologous series based on the general formula from their molecular formula. Now, there could be more than one substance here, because remember, something with the same molecular formula could have a different structural formula and therefore have different physical properties, different chemical properties, and we need to be very aware of that. So what's the first question? Write down the name of the homologous series, and we've done it already, to which Q belongs. So Q, we've looked at the molecular formula, and we recognize this belongs to the series of alkenes. Just to remember, it belongs to the alkene family or the alkene homologous series. And if they asked you for a reason, the reason would be it has the same molecular formula as the general formula. Formula. And what would we be expecting? We'd be expecting something with a double bond. One double bond in that substance. Now, it tells us something else now. It's asked about Q. We recognize that P isn't the same as Q. We've identified it as being an alkane. So let's be very clear about that and just remind ourselves that this is an alkane. It doesn't have a double bond. It has single bonds all the way through. It tells us that compound P reacts with chlorine to form 2-chlorobutane. So we have an idea about the formula. They've given us the IUPAC name. Now, what they ask us, first of all, is to write a balanced chemical equation using molecular formula for the reaction that takes place. Now, notice what it says. We've got compound P, which we now need to identify. It forms 2-chlorobutane. So we know it was a hydrocarbon, so that must have been a alkene, so it was butane. I'm just putting it in words, plus chlorine, so I don't make a mistake, gives us 2-chlorobutane. And we are going to have something else left over as well. It's going to be hydrogen chloride. Now, that is just to try and guide me so that I don't make the mistake. Let's put down the formula. But would be 4-ane H 10 plus Cl2. Remember, chlorine is diatomic, so we can't just have Cl on its own. It's a chlorine gas. We're going to bubble these two gases together. Butane at certain temperatures may even be a liquid, might be bubbling chlorine through butane. And we're now going to make a substance where one of the chlorines exchanges positions with the hydrogen. So we're going to get C4, that stays the same, H9 Cl, and we're left over with HCl, hydrogen chloride. So there's your balanced equation. Check that you've got the correct number of chlorines. You started with 2 chlorines, you're ending with 2 chlorines. You started with 10 hydrogens, you're ending with 10 hydrogens, and so on. And we've balanced that. What type of reaction is this? Well, this is clearly a substitution reaction. And why do we say that? Well, one of the chlorines has taken place of one of the hydrogens, and we're left over. Now, the last part of this question says, what reaction condition, other than the need for a solvent, and that's where they're saying there's something that this has been dissolved into, because it might not be easy enough to do them as just gases. What do you need? Well, you're going to need, for substitution, heat or another form of energy. And the most common one is UV light. Okay, guys, I think that's time for a break now. We've looked at one type of reaction that's taken place, and we've looked at one of the exam questions. Let's take a break, and after the break, we'll be back to do some more. Hi guys, welcome back from the break. Hope you've got the ideas of chemical reactions or organic reactions going clearly in your head. Let's go on to the next question and make sure that we're getting it right as well. So we're dealing still with P and Q, but this time it tells us compound Q takes part in reactions as shown in the flow diagram. It's quite often that you'll find organic chemistry reactions illustrated as flow diagrams. You need to fit together the missing bits and pieces, identify as much information as you can. So remember, what I find useful here is to start by indicating the information I know. So compound Q, remember earlier we identified that as being an alkene, and we recognize that that's got a double bond. It is unsaturated. We're told that reaction 1 happens with bromine, and it produces for us 2,3-dibromobutane. So let's just quickly identify what's happened. Notice we started with 2 things and we've ended up with 1 thing. So without much doubt, we know that that's an addition reaction. And it's typical because you've got 2,3. And you've got that process taking place. The double bond was between carbon number 2 and carbon number 3. And we've simply added the bromine across there. Now, what about in this reaction here? We recognize that we're getting 1 product again, and that's going to be, what is it? It's the alkane, isn't it? It's just simply butane. Now, let's go and see what they're asking for us. It says, write down the structural formula for 2,3-dibromobutane. Well, to start off, but means 4. So 1, 2, 3, and there's my 4th carbon, all in a nice row. We need to recognize that each of these carbons has 4 bonds. And I don't want to put anything in at the moment to indicate what else is bonding with them. What we need to do is to do the numbering. I'm just simply going to number from left to right and say that's number 2, that's number 3, and that's number 4. And it now tells me that it's 2,3-dibromo. So there's a bromine that's sitting over there and a bromine sitting over there. What are all the other things going to be? Well, they're going to be hydrogen. So each of these carbons has got a hydrogen partner, and in the space that I've got here, I'm able to fill that in. Please draw carefully and neatly so your examiner's not guessing. Make sure you indicate the bonds between each of them. Now, the last part, the next part at least, we've already done because we were asked to identify of compound Q. I beg your pardon, we haven't done it. We simply know that it was an alkene. But we haven't identified its actual name. What we do know is the double bond was between the carbon number 2 and carbon number 3, because that's where the bromines went in. So it was an alkene, so it was but. But where was the double bond? Between carbon number 2 and 3. So on 2 is the lowest number, so it's but2-ene. We need to write down a balanced equation using structural formula for reaction number 1. Guys, when you ask structural formula, please don't write molecular formula, and when you're asked molecular formula, please don't write structural formula. You have to draw them out. And because structural formula takes some time and takes space, I'm going to write them a little bit bigger and write it down below. So I'm going to start with carbon number, the substance I'm starting with, which was Q, which is but2-ene. I'm going to write the structural formula for but2-ene. There it is. Put the double bond in on carbon number 2. The hydrogens all fill in. Now notice I can only put 1 hydrogen in on each of those positions there. Now, the next thing, it's for reaction number 1. So we know the end result is butane. So I'm going to write down that formula for butane, and I'm going to put it over here, just so that we've got space to see both of them on the same page. There's 4 carbons, and butane is saturated, so it has 4 carbons and all the hydrogens in. Just make sure that I've got them. Let's count them: 3, 4, 5, 6, 7, 8, 9, 10. And we've got them right. So what's different between the substance that I've drawn in pink, Q, and the product of the reaction number 1? Well, it's clearly that there are 2 hydrogens that are missing. And that means I draw the structural formula of the hydrogen with the hydrogen shown, the bond between them, as in a line like that. And what's happened? If we were asked to explain it, the hydrogen has added in that position. So these 2 hydrogens were originally part of the gas, and they've added to the process. They've added to the substance. We're asked what type of reaction occurred, and we could call it hydrogenation. Or we could just simply say it's an addition reaction where we're adding hydrogen, but it's preferable to say hydrogenation. We're adding hydrogen, and that's the important thing. Let's move on to the next question, and we're just going to start this question, and then we're going to go for a little break. First thing, it says the flow diagram again shows the steps that a learner follows to convert but-1-ene to but-2-ene. Now look where it takes us. Analyzes but-1-ene. Now remember, but is 4, and the ene tells us it's 2 times 4 is 8. It gives us a product. Then it gives us something that's got a hydroxyl in it, and then it gives us but-2-ene at the end. That's quite an interesting process. Wonder what's happened in between. Let's see what the question asks us and make sure that we've got these things sorted out. First thing, it says write down the structural formula of the functional group of but-1-ene. So there is but-1-ene, and we need to get the functional group. Now, guys, you don't need to draw the whole structure. It's just the functional group. And I don't think there's too much difficulty in saying the functional group is just going to be those double bonds like that. Okay? The double bond between the 2 carbons, that's the functional group. Now, the next question tells us that compound X is formed when but-1-ene reacts with HCl. So X, let's get it clear, this forms from there to there when we've reacted with HCl. That's quite interesting. Hope you can see what's happening. So name the type of reaction. The first thing that we need to do is to name the type of reaction. We're going to do that. It is an addition reaction because it's breaking the double bond, and we could even say hydrohalogenation because we are going to add to the original substance a hydrogen and a chlorine. It asks us to write down the structural formula, but I want to go a step further than that. I want to go down here, and I want to just show you how that process takes place. So we're going to start with but-2-ene. It was but-2-ene, but-1-ene at least, but-1-ene, and let's see how this works. There's the structural formula. Now, there are 3 bonds there. There's only place for 1 more, and we're going to put the 1 down at the bottom. So along comes hydrogen chloride, hydrogen and chlorine. And we want to take the hydrogen and the chlorine and add it to the double bond. That means we're going to break one of these bonds, and we're going to just be left with one of them. The other one is going to appear at the top over there, and the other one is going to appear at the top. Now what happens in that case is that these ones just move down a little bit, and this one moves across just spatially. So that where we're going is that this hydrogen here which I was hoping wouldn't happen, that it was going to be 2 bits, but this hydrogen and chlorine comes and sits over there like that. Now, let's pick up the eraser. They can't all be bonded. That one breaks off, and these ones just become realigned so that the spatial features are a little bit better. So I'm just going to erase that bond, and it doesn't like me doing that. I want to just do that and then fill it in my green pen and say that one's got there and this one has got a little bit straighter, and we're going to fill that in as a straight line. And there we've got it. We've got the structural formula and the process of adding it together. So I hope you can see that that whole thing has worked out. We just put it down there. That's the structural formula of the substance. Now, it asked us to draw write down the structural formula of X, and we've gone and done that. So I think we've answered that question. You know what? I think we need another little break before we finish off this question, and we'll be back after the break. Make sure you stay tuned. Have a look at question 2.3 during the break. Write down what you think the answers are, and then we'll confirm them when we get back. Welcome back from that break. I hope you've been thinking about 2.3. Let's just remind ourselves what we've established so far. We recognize the identity of compound X, and let's go and read what 2.3 says. It says that X is converted to alcohol Z. So that's where we're looking at. We're going from this position to that position. We're asked to name the type of reaction that takes place. Now remember, this is our compound X over here. This is what X is, and we've identified it earlier as the one that we haven't actually named it, but we recognize that this is bute, and it's at carbon position number 2, so it's 2-chloro butane. And that's what X is. Let's see what Z is. If you look at the condensed formula here, and you get right in over there and you look, you'll see that on carbon number 2, we've no longer, that's carbon number 1, that's carbon number 2, we've got this hydroxyl group. That's carbon number 3, that's 4. So we've changed it from being a haloalkane to an alcohol. The OH gives us a different structural, gives us a different functional group, and it's now an alcohol. So we would name this as bute. So carbon, the name, the IUPAC name would be, it's still bute because it's still got 4. So bute, but now it's butane. Which number is it on? The alcohol on carbon number 2, and we'd end it as butane-2-ol. Always give the position as a number in the name. That's what the IUPAC requires it. And so you see, it don't say bute-2-an-ol. No, that's not right. We want to give the number to the ol part. The ol is the alcohol. So, guys, what's happened? If we started with this thing that we've drawn in yellow, the chlorine, and we've simply replaced it with an OH. So we've taken that, we've taken it away, that chlorine, we've taken it away, and we've placed in its place the hydroxide, or hydroxyl at least. Don't call it hydroxide. Hydroxide is for acids and bases, and we call it in organic chemistry hydroxyl because it's bonded to the carbon. The hydroxide is an ion with a negative charge. So please get that terminology right. So there's your alcohol now. So what's happened? The one has taken the place of the other. So the answer to our question is name the type. It's substitution. So we've dealt with addition, we've dealt with substitution, and it now says just write down the name or formula of another reactant needed for this process. So if I'm going to make this happen, I'm going to start with my X, and I want to get something in that's going to give me an OH. What's a source of OH? Well, there are two options. You could say water is a source of OH. Yes, it has. It's H2O, so one of those OHs could get in. But the other one is weak, or a dilute solution, sorry, not weak, dilute solution of something like sodium hydroxide. So what happens is we get a substitution taking place. The chlorine coming out and the OH going in, and the chlorine then links up with the H to give us the other product of this substitution reaction, and we would get that plus HCl, or if we were using the sodium hydroxide, we've got NaCl. So there's the substitution going on. I hope you can see that. Please make sure that you understand this very well. Now, we've got another part to this question, which is probably the most interesting part. It's winding up on how we go from the alcohol to the final product, and then there's a little twist in the tail that we're going to deal with as well. So now our focus is on going from Z to butene. So we're dealing with alcohol going to an alkene. What does it say? It says Z is converted to butene in the presence of concentrated sulfuric acid. Now, then they ask you some questions. It says, is Z a primary, secondary, or tertiary alcohol? Let's get some space to explain the difference between those, so we can be very clear about it, and we can then put it clearly. So we've got the bute, and it was, and position number 2 was where the alcohol was, or the hydroxyl group, and I'm just putting that in like that. Now, what I need you to understand is what's the difference between primary, secondary, and tertiary alcohol. When you look at where the OH is, where the O is bonded to the hydrogen, what I want you to do is to circle that carbon. Once you've circled that carbon, you then say to yourself, how many partners, how many carbon partners does that one in green have? Well, look over here. It has one carbon over here. It has one carbon over here. This means that this is a secondary alcohol. You say to me, okay, so the carbon that the O is bonded to two other carbons. So what would a primary alcohol be? Well, it's not that difficult to do. Let's see if we can do it with this board. That was the secondary. Let's move our hydroxide or hydroxyl, making that error too many times, but it looks like that's grouped together. I'm just going to use the eraser. If I took that one out and I swapped it and put this one in its place, I'm now going to put the O there, the H there, and put that H over there. Now, do the same thing as what we said before. Let's circle that one. How many carbon partners has it got? This one has only got one carbon partner. So this one is a primary alcohol. This one is primary. It's primary because there's one other carbon. All the other things, the other two possibilities are hydrogen and hydrogen. It's not carbon. So primary alcohols are those that are on the ends. What about a tertiary alcohol then? Let's compare that very quickly. If we had, and I might not draw the bute, draw a prop, and if I had a methyl over there, then if that were the situation, then this will do the same sort of setup to determine the nature of the alcohol. Circle that. how many carbons are around that green one? 1 carbon, 2 carbons, 3 carbons. 3 tertiary. Okay, I hope you can see how to do that, and that should make us very clear about what that answer is. The answer that we want to put down there is that this one happened to be a secondary alcohol. Only put down the name that they've asked you, a secondary alcohol, and it's only 1 mark in any case. Now, we've asked to name the type of reaction that's taken place to go from Z to butene. Well, is converted in the presence of sulfuric acid. So let's just take a look at where we were. We had our secondary alcohol, and we'll get to it, have it up on the board again in a minute. There we go. There's our secondary alcohol. Let me just fill in those missing bits. And what we're going to see happen is that we have moved from that position to having butene. We were at but1ene, we're now at but2ene. So look what's happened. That has been circled, that's been selected, and we are extracting that. We're eliminating it. So the type of reaction that happens to get to but2ene, we've got to get rid of the OH and an H. We're eliminating water. So we can say it's an elimination reaction. Okay, it's elimination. Elimination. The other word that we can use, because it is removing water in this case, it's what would we call water? Dehydrooxygenation. So we would recognize it's removing water, eliminating water and forming the double bond. And what role is the sulfuric acid in this? It is a catalyst, but it is also known as a dehydration. And that's probably the word I was looking for that I couldn't get. Elimination, dehydration. Let's put that, dehydration. So hydration, adding water, dehydration, eliminating water. Now, let's go to the last part of question 2, which says a learner discovers that but2ene can be prepared in another way. So there is another route. Instead of going from compound X to but2ene, there is a second way of doing it. And he suggests that you start with compound X. Remember what X was? It was, with the chlorine in it, it was but2-chlorobutane, and we then were able to recognize where we're going with that. He's suggested that there's another method. Take X, add something, and you will be able to get that and that and that. So here is another route. Write down the type of reaction that takes place. Well, we need to just identify X and make sure that we've got it right. We did this earlier, so I just need to look back on my notes there and see that we started with 2-chlorobutane. We've started with 2-chlorobutane, so we went 2-chlorobutane, and we've ended up with but2ene. So what sort of reaction have I got? I hope you can see that the chlorine is the central thing here, and we've formed a double bond. So what's been eliminated? What's been changed? It is the formation of a double bond. When you form a double bond, it must be elimination. So we recognize it's elimination. But if we wanted to be specific, what's been eliminated? What we would say is that we've taken away HCl. And so we would say this is dehydrochlorination. Dehydrochlorination. Quite a mouthful, that one. So what are the products? What are we going to need, and what are the conditions that we need for this reaction to take place? We've said elimination, which is good enough. What are the conditions? Well, guys, to eliminate under these conditions requires energy, but it requires a certain pH as well. You're going to have some concentrated sodium hydroxide, and you're going to also need heat. You're going to need to heat. And it doesn't happen very easily. So the last bit of this equation that we need to do is to recognize the substances that are involved. So where we've got that word equation, I'm just going to add in the substances below it. So what is A? Well, we're going to start with compound X. We're certainly going to need, to do this elimination, some sodium hydroxide. And the second thing that we're going to do is we're going to make the butene, yes, but we're going to also make sodium chloride, because the OH gets put on, the Cl gets pulled off, and the last point is that we're going to end up with some water as well. Okay, so I hope that's made that sense of that. We've got one last question to do, and I think it's very important that you study this question. We haven't had polymer questions in previous exam papers, so I've just pulled this one together, but let's make sure we concentrate on making sure we understand this particular one. We're told that we've got something called polylactic acid. It's an example of a polyester that's formed by condensation. Remember that there are two processes to make polymers. One is addition polymerization, something like or if we take ethene and we add ethene to ethene many times, we'll add those, break those double bonds. We're adding them together. It's called addition polymerization. Now we're doing condensation polymerization. So where do we start? It says draw the structural formula of the monomer used to produce polylactic acid. So the thing I need to do is I need to draw the structure of lactic acid. So let me get that out in front of me, and let me draw it over here. So this one you're going to have to learn, and I've had to learn it as well. So we need to recognize that it has a carboxylic acid end to the one side. Now check the number of bonds. 1, 2, 3. This one can go on to there. In the chain, there are only 2 bonds. The one end is a carboxylic acid. The other end is an alcohol. So 2 carbons, and with that in place. Now, the other trick is to remember on that second carbon, then there's also a methyl group. And that's your structure of the monomer, lactic acid. Okay, it's not a very easy name to work out. You can't work. It's not an IUPAC name that you can break it apart. You're going to have to learn. That's lactic acid. Of course, lactic acid occurs in our bodies, and we need to recognize that's what makes the polymer polylactic acid so useful, because it can decompose in an environmentally friendly way. So now illustrate, the second part of the question says, illustrate the reaction to produce polylactic acid by showing how 2 monomers combined. Now, I haven't got much space here, so I'm going to redraw this one a little bit more closely. So remember, it's the hydroxide followed by the carbonyl, followed by another hydrogen, followed by a methyl group, and we can just repeat this unit on the other side. Over here is my alcohol, and now I'm going to draw in a different color, the same thing as I had earlier. I'm going to now put this one into this position, HO double bond CH3, and you can see you can go on forever with this sort of arrangement, OH. Now, what is going to happen? I hope you can identify that this end is an alcohol, while this end, this functional group, is a carboxylic acid. And when those two come together, the alcohol and the carboxylic acid, that's forming an ester bond. So we're illustrating how that happens. They're going to dehydrate the water. We're going to take away water, and I'll put that like this. If we pull that away and we join them together, then we're going to get the overall structure of the substance, where we'll go on this side. In fact, what we can do is we can simply take that H off, because we're just wanting to show 2 units, but I'm going to leave the H because we know that that actually carries on doing it. Missed my pen. And we've got the double bonded O there, we've got the C, the H. Now the O followed by a C, that's the O, followed by the C, followed by the carbonyl, followed by the H. And now we just need to put the methyl groups in, and the methyl group goes in over here. And on the last one over there, methyl group, and right at the end we have another O. So there's the joining together, and you can see that this can then extend and repeat itself numerous times. We've shown the process of the alcohol end combining with the acid end. Well, guys, I hope that you have followed this particular example of condensation polymerization. It's something you need to know. You need to study it hard. Wish you all the best for your organic chemistry. From me, John, goodbye.